Perfect. All right. Okay. Cool. So we have this fancy paper. The title is too long, so I'll just skip over it. We'll come back to this. Let me start off with a question. Say you want to get manicure. Which one do you want to get? Okay, so you don't want manicure. What about your guys? Well, if you were paying attention to class, then you'll know that the one on the right is going to be easier to get some photometric stereo out of it. And if you really want to get it, there's a product link down there. But there are limitations to photometric stereo, like the picture we saw right now. And it doesn't really work well for shiny things and semi-translucent things. By the way, I took this slide from yours. Thank you. And wouldn't it be so nice if we could somehow solve all of these problems? And today, I have a solution. Well, actually, not all. It doesn't solve everything, but first of all, it solves these issues with the first innovation through material engineering and hardware. And then it solves all of these problems using the second innovation, the algorithm. And we'll go over them step by step. So the first part is we want to solve this problem with changing the material. So we have specular translucent things. How do we find the geometry of translucent things? Well, we talked about it in the previous presentation that we can paint over them with matte paint. So this is not the perfect example, but you can see that the paint made the cup less translucent, and that way it's going to be easier to model the geometry of the cup. Another the example is you have different wall paint. So if you have a semi-glossy wall paint and you want to somehow model it, you might want to paint it over with a flat paint. But that has another problem, that it is too permanent, it's destructive, it sticks onto the wall for too long. So the solution here is we can wrap it with something instead of painting it, so that we can take it off later. So I don't know if you see these YouTube videos, I do all the time. This person is wrapping a car with a vinyl sheet, and that makes this glossy area less glossy and it's more matte. So that can help with modeling the geometry. But there's another problem. The sheet covers all the small microplastics, and you can if you want a 3D model to like drive this car around in a game, then probably this is good enough because it has all the large structures. It keeps all the large structures, but if there was a dent in the car plate, then we wouldn't be able to see that. So what's the solution? We could dust the surface lightly, and here, I don't mean removing dust, but I mean actually covering it with dust, like this. This is a table it's a lacquer table, so it's usually shiny. But if we dust it, if you leave it out outside for a long time, you can see that it becomes more matte, right? And you probably tried this when you were younger, when you would put like graphite on your finger, and then you could stick it onto the tape, and you could kind of model your fingerprints. So, but then the problem with this is we need to do this every single time. So how do we make it more reusable? Today I present the GelSight, which is the topic of the paper. And this is a part. This is the center part of the GelSight. You can see the fingerprint pretty well over there, right? How this actually works is this is a larger version of it. There is a thick layer of transparent gel, which you can press into, and then there's a thin layer of reflective pigment or powder that sticks onto the gel, but it doesn't stick onto the material, onto the object itself. So we can reuse this on and on. So let's look at how they actually set up their device. So this is the same photo, right? And this is a exploded view, so it's kind of separated everything. And so align it with the image, I'll rotate it. And you can see that the object with the finger presses into the pigment in the gel sensor. And we're going to take an image of it from above while illuminating the entire glass plate from all sides with the 6 LEDs. And so each LED is going to like shine down at the center a little bit. And the question arises, why do we have several lights? If we have like an example-based photometric stereo, that the lookup table method, that we could, in theory, we might be able to just get away with using one light. But because our diffuse material facing the other direction is darker, it's harder to model. And also, there are shadows. There are shadows because this is not a distant light. There are occlusions that happen when you get really up close. And we're trying to get at the micro passes. So there's a lot of shadows going on. So we would like to get images from all the different angles. So this is an example. This is an image of a coin with 4 different lighting directions. And we're going to somehow combine these to get the geometry out of the Okay, so that was the materials and the hardware innovation part of it. And it could, using the powder, it can coat the shiny and semi-translucent things. And it also solves a little bit of reflections because it's less shiny, right? And the material that they picked, the powder that they used, was carefully picked out of different candidates to have as little interreflection as possible. So part 2. Now, how do we approach this with the algorithm? So this is the standard traditional photometric stereo algorithm. We have we assume that everything is conversion and we have a distant light source, so we can model it with this equation that we saw in class. And then using that, we're going to reconstruct the surface by integrating the surface normals. But in our case, we don't have a distant light source. The light sources are really up close. And so if you look at this image, you can see that the lighting direction is different for different parts of the object, because the light source is somewhere over here, and the light source is too close, so you don't have parallel light rays. So how do we account for that? We're going to calibrate the lighting direction. So and this object is something we actually created using 3D modeling, so we exactly know what the shapes are like. So what we're going to do is we're going to take each of these circles here, and we know they're normals. So what we want is the light direction at each position of the spheres. And the blue dots on the right are the positions of the spheres. And for each sphere, we can solve the equation to find the values of L. And yeah, so on the right, you see 2 coordinate values of L for each position on the XY plane. And the authors, what they did is they modeled this curve, and so that we can interpolate for the areas that are between the spheres. And why do we need to interpolate? Because we are going to switch out these spheres with a different object, and the different objects are going to have a lot of detail in between these areas. So that's why we want it. Okay. So from what we calibrated in the previous slide, we are going to now we're able to So now we have the L's for each point in the object, on the object. And we have the light intensity from the pixel values that we're going to get. And for a new object that we're going to see, we're going to calculate the normal, surface normal for each position separately. And then, and then we'll reconstruct the surface. But then, because this is a complicated system, there are a lot of different steps that go into this. And the first pre-processing step is the median noise reduction. And what this does is it accounts for the small dust particles or like small cuts in the gel. And what we're going to do is we're going to rotate the gel so that the scan varies. And this is a more intuitive way to look at median noise reduction. So let's say we want to get rid of this annoying torus in the photo. So we take a lot of photos at different points in time. And if we find the median value in the square, what we get is that. And this actually performs the median value over the entire image. So this is a good way to get rid of noise if you can somehow make all of the images perfectly aligned. So there's a limitation. It needs to be perfectly aligned. And even then, you can see some artifacts over here. People are like walking around. You can see like ghosts of their image. So that's a slight limitation, but we'll do that. And then we'll go on to the linear estimation part. This is what we know how to do. But then in real life, and especially in our case, the surface is not perfectly convergent. So what we are going to do is we're going to steal an idea from spherical harmonic shading that looks good, and we're going to model the normal again. So we looked at this already. We calibrated the values of the lighting directions for some positions, and this is the more sophisticated nonlinear model that we have. It's a quadratic model with regards to the normal. And similarly, we're going to calibrate for the values of the coefficients A and C. And then in the linear case, we would use some linear algebra. We would do like pseudo inverse on this to get the surface normal. But on the quadratic model, we can't really do that. So what we're going to do is we're going to keep on updating the values of n using Gauss-Newton or other iterative model methods. And we'll take the value of n from the linear model as a starting point. So that makes it look better. But then there are still shadows in the image. This is kind of easier to solve because we took a lot of different images with different lighting directions. If we think that there's a pixel that is too dark, we'll just think of it as a shadow, and then we'll discount it with a weight by giving it a weight of 0. So for example, over here in the bottom, there's a shadow, but then in some of the other images, that's not dark, right? So they'll just use the brighter images instead of the shadow. So using our algorithm, we managed to solve these problems, which is cool. And
Whiz. All right.
Yeah. So let's see if we pay attention to our presentation. Actually, this is very unrelated to the actual content. The quiz is, what is this object? Skin. Okay. Specifically, what part? That's probably part. That's the thing. Okay. There's another object, which is also a human skin. You probably know. This is a bug. This one. Can anybody guess?
Hopefully not human skin.
Maybe some dermatological issues. I don't know. This is actually the sticky side of a Post-it, and the the spherical objects that you see are the blue, and all of these are the paper fibers. And the diameter of this is like 100 microns, which means the entire image is like a millimeter by millimeter large. So this almost looks like it almost gives the impression of an electron microscope, but it's way more portable and faster, and it doesn't have to be done in a lab condition. That's what this one is.
Gecko?
Sorry.
Is it the gecko?
The gecko skin.
Yeah.
It was an animal. It's a feather. And this one. You've probably seen this. Maybe in the last week. This is actually from $1 note. Specifically, it's from the treasurer. So this method, although you can't even feel the texture on the paper, it gives a really nice geometry. And this one, it's not a crater. This is actually from a bullet that was fired. I guess you could use this for forensic science. And so going on to the numerical results. So does it actually work very well? So the image on the top is a slice of a 3D object that it's an actual slice, and they photographed it so they can figure out the actual geometry, which translates to the red dots in the diagram below, and it matches pretty well. But if we were to use a linear model, then it wouldn't be so perfect. So all of the algorithms that we did, the quadratic model, was actually helpful. If we didn't even use that, and if we just used a lookup table method, then it would have been even more. Anyway, so that's the results. But some unresolved questions I had while preparing for this presentation was, in this image, I believe this is a single lighting condition, but there are these staircase effects. I don't know if you can see from there. But I couldn't find out why that was happening. Maybe it was some issue with reflection. And also, I would have liked to bring you some physical basis of why we're using a quadratic model, apart from the fact that it just looks good. But there's a whole area behind this, so feel free to look it up.
We might look it up.
And to summarize, this method is cool because it accounts for shadows and it uses a lot of innovation and materials as well. And as a result of that, it can be fast, it's portable, has micron scale resolution, which is useful in some cases. And it's also PRDF invariant. Maybe that's a good thing, maybe that's a limitation. These are the ones that I can think of. You can use it for manufacturing, quality assurance, like detect dents or scratches in spaceships. You could do counterfeit bills, or you can use it for biomedical imaging, like modeling your teeth. Some limitations that this has is so this is not very good for sharp corners. So because it's a gel, it can't get into all the nooks and crannies. So it can't model sharp corners very well. And this is tiny, so it can only model in a small area. And it requires contact. It requires physical contact. So you probably don't want to do this on the model. And the gel material, I did tell you that we can reuse this. We can, but after several uses, we to replace it because it's going to like get dust on it or like break apart. And because we're using a single powder pigment, we can't really model the color. Somehow. And in the spirit of brownish Rosnar, I think we can do slightly better by scanning a larger surface by stitching multiple stems. Thank you.
Great. Really nice job. A lot of elements that I really like. I thought your motivation was really stellar. One thing just to point out, nothing really specific. 6 minutes over 15, so it's 21 minutes. Things that it's totally fine. But in the future, if I see that, okay, well, we need more time. I reserve the right to, step in. All right, okay, wrap it up. Maybe I should flag. But it was a really, really nicely. So how many of you have actually, before like you read this paper, how many of you heard about GelSight before? Oh yeah, okay. So technically what Steve working on GelSight. So Wenzen one has been working on GelSight for a while. And specifically focused on the robotics side. So it is trying to think about robot arms where the fingertips are all GelSight, so that you can go and grasp something and then have some sense of what are you touching? How does it feel? What's the texture? Is it something that's slipping? Do I need to put more pressure or less pressure or something like that? So they call these tactile sensors because, well, it's sensing through touch. You need to make contact with the object in order to actually see it. So, I think companies, startup companies based off of this idea. So this was really early on, right? A couple of years after. So they presented the first work, I think, in 2009, and then a couple of years later, they had a version that was more focused on all these different challenges and focused on the entire pipeline for coverage. But things have progressed since then. A decade later, technology is better. Most things fine. Any ideas what people have been just looking at? What kind of other innovation? How can you extend this? Besides, I like the idea here of scanning surface patches. So there's a trade-off here with, okay, if I can zoom in and I get this microgeometry, but now I have another microgeometry. But maybe stamp the surface of the application. Get a large field of view, but also that like high precision. There are other ways to potentially extend it. So roughly half of you wrote something about this. Do you have any ideas how you can take this work and extended in some way, questions, 6 formulas.
Some type of gel that could go under the skin and have some light to try to recover the structure under the skin or something.
That's an interesting idea. Now, putting it, yeah. Well, you hit on something that's a really challenging problem, and it's something that if you can do imaging under the skin, that's immensely helpful. Now, inserting gel underneath the skin sounds a little scary. But people do put things in, and so there's all sorts of imaging techniques where you do insert something in a body. This might include putting some kind of radioactive dye and using a PET scan, a complicated device, but that sees basically where that dye is. Or you might put certain beads that will, when illuminated, will fluoresce a certain color. Or maybe you take non-invasive ways to other invasive ways that put cameras on long fibers certain endoscopes. So although it might sound a little bit crazy to put gel underneath the skin, it's certainly possible. People have done that. Sometimes it's necessary in order to make sure that, well, if I'm operating on someone, that I'm not going to make a major mistake by cutting the wrong part. Imaging in the body.
It's a direct use case of what you said. If people have like fragmented bones, broken surgery, and if it's fragmented into too many parts, then you would like to get as many out of your body as possible, but then they will be covered in blood, so which will be harder to see. But I guess this.
Maybe. One, I think, cool is that people have been doing. I think one is to add texture to the GelSight panel. So what we're seeing in this version is changes in the surface of that texture, right? So it's a kind of a photometric stereotype approach where we're looking at different normal orientations. But there's more to the deformation of that surface. It's not simply the surface going up along in the Z direction. Things can potentially shift laterally. So if I were to hold something up with the GelSight, this object might be pulling down on that GelSight pad and deforming or basically shearing that pad. So imagine taking one of these GelSight pad and paint it. We also add maybe a grid of dots. So what the camera would see under natural conditions is just a grid of dots on the sensor. Now, if you press that down, maybe at an angle, those dots may shift somewhat. So it's a certain amount of shearing. So perhaps it can be used to identify the forces. Another potential way, or maybe you can use I don't know what this is actually, but maybe you can use the fact that, well, the camera typically is focused on this GelSight pad, it's assumed to be in a position. As you go further away from that position, things can get defocused. So what if you use these dots, these grid dots, and measure defocus these dots to figure out not just normal orientation, not just shearing, but maybe displacement as well, getting some sense of better sense of depth. So any depth that's recovered here is usually done through solve this, take into account particles, shadows, integrate normals, and get some geometry out. But it's still geometry from maybe or other depth views. Any other thoughts?
The question: how to find the best material to paint it, and how to find the best light setting corresponding to.
That's a really good question. What is the best configuration? I don't know the answer to this. Certainly, this is something that I want to try to fully engineer a system as possible. What is the right? What is right lighting positions? How thick should this gel pad be? How wide should it be? These all play. There's other source of complexity here, which is potentially captured in this reflection filters. These are things that are not super trivial to kind of figure out. So what people have been doing includes trying to come up with a simulation that will basically generate a GelSight sensor fully convergent. You try to model all these things. And then maybe you have some kind of metric that says, okay, under realistic noise settings and realistic materials, I can kind of evaluate what is the output of such a sensor. try to design, maybe with some human, like try to, or maybe some design positions of these light sources, try to select different materials to help you refine this process. It's not obvious what is the right set of solutions, what are the right parameters. My go-to would be, well, if you can get it to be in an ideal photometric setup, photometric stereo setup, perfect version of stereo, that seems like a pretty good kind of formula, because we know that with photometric stereo, you'll need light sources working information, need light sources that and then if I can get a perfect light version surface, 3 light sources that are distant, everything's, I know what to expect. The real world's a little bit more complicated because when your light sources are close, right, you can't get this distant light sources. You have these reflections. So and then it's kind of opens up this thing. So I'm not sure. I think that the answer is to kind of drive it from the curve of what works best, right? And maybe try to optimize it. I would probably avoid the metallic surfaces for sure. Things that are more diffuse, but not fully diffuse, where no shade variation. That's not so interesting. Very speculative. It provides a lot of shade information because that spectral point is really good. Right here is what it's in direction. What that means is that you need lots of light. Some balance. All right. So I think those are